In the natural world, purity is an illusion. Almost everything you encounter, from deep seawater to thick crude oil to the soil under your feet, is a complex, chaotic mixture. Nature does not hand us isolated elements. To extract the pure from the messy, we rely on experimental chemistry. It is an exact mathematical science built entirely around the ability to forcefully separate these chaotic mixtures into isolated components. But before any separation can happen, a strict baseline of control has to be established. This framework is known as Good Laboratory Practices, or GLP. These rules are non-negotiable because they prevent the mixture's chaos from becoming a physical hazard. For example, when diluting concentrated acids, you must always add the acid to the water, never the reverse. Adding water to concentrated acid triggers a rapid exothermic reaction that can instantly boil the water and shatter the glassware. Mastering these safety procedures is the mandatory first step. You have to establish absolute physical control over your environment before you can begin to impose chemical order onto a mixture. We begin separating mixtures using physical gatekeepers. The most basic of these is filtration, which separates materials purely by exploiting the difference between the size of a solid particle and the pore size of a filter. A standard gravity setup uses fluted filter paper to maximize surface area, letting liquid slowly drip through. But when time is a factor, we upgrade to vacuum filtration, using a Buchner funnel, pulling the liquid through rapidly via negative pressure. Physical filters fail, however, when a solid is completely dissolved in a liquid. To separate these, we turn to crystallization, which forces the solid out of the solution by manipulating temperature-dependent solubility. This graph shows the solubility curves of 3 hypothetical solvents as they are heated to a boil. The primary challenge in crystallization is identifying the exact right solvent for your target compound. Look at solvent C. At room temperature, it dissolves almost nothing, but at its boiling point, solubility spikes. This steep curve is exactly what we want. We dissolve our impure mixture in boiling solvent C, and as we let it cool back to room temperature, the liquid can no longer hold the target compound. The pure substance crashes out as solid crystals, leaving the impurities trapped in the cold liquid. For highly volatile solids, we bypass the liquid phase entirely through sublimation. When heated, compounds like iodine instantly convert from a solid directly into a gas. The vapor rises, hits a cold surface, and deposits back into pure solid crystals, leaving non-volatile impurities resting at the bottom of the flask. By identifying the specific physical states and temperature thresholds of a compound, we can mechanically strip away everything else around it. When physical methods aren't enough, we rely on chemical affinities. Solvent extraction is governed by the partition law. We use this when our target solute is dissolved in water, but has a naturally higher chemical affinity for an organic solvent. This diagram illustrates a separating funnel at work. The two liquids do not mix. Because the solute strongly prefers the organic layer, shaking the funnel forces the target molecules to migrate upward. Mathematically, the partition law dictates that performing multiple extractions with small volumes of organic solvent pulls out exponentially more solute than doing one massive single-volume extraction. To separate the most complex invisible mixtures, we set up a molecular race called chromatography. The competition happens between a stationary phase, like a piece of paper, and a mobile phase, which is a liquid solvent creeping up that paper. You can see the results of this race here. As the solvent travels upward, it drags the mixture with it. Components that strongly bond to the paper drag their feet and stay near the bottom. Components that prefer the solvent race toward the top. The differences in affinity pull the mixture apart into distinct visual bands. We quantify this race using the retardation factor, or RF value. You simply divide the distance traveled by a specific compound by the total distance traveled by the solvent front. Because every chemical has a specific RF value under fixed conditions, chromatography provides the mathematical evidence needed to identify a substance while physically separating it. These 5 foundational techniques, filtration, crystallization, sublimation, extraction, and chromatography, are not isolated classroom exercises. They dictate how global pharmaceutical labs synthesize life-saving drugs. The exact same logic that isolates a few milligrams of a compound in a glass flask scales up to run massive civic infrastructure, like these industrial filtration and sedimentation tanks treating millions of gallons of municipal water. Filter the insoluble, crystallize the soluble, sublime the volatile, extract the organic, run chromatography to map the complex. By applying the precise mechanics of separation, you stop being a passive observer of natural mixtures and gain the exact tools required to build, isolate, and guarantee pure matter.